Good morning, students. Welcome back to experimental stress analysis classes. And today is class 5. And today we will be discussing about the 2D photoelasticity and 2D photoelasticity materials. So, in the previous classes of photoelasticity, we have learned that how the photoelastic material exhibit the refraction, what you call as double refraction, and numerous materials have been employed in a photoelastic analysis. And here in this session we will discuss what are the different photoelastic materials and what are the photoelastic material properties. And there are many different materials which will be considered as photoelastic materials, and which include the Columbia resin CR and Homolite 100. Third one is a polycarbonate and epoxy resin. Along with this one we have urethane rubber. So these are the major different types of materials which can be considered for a photoelastic analysis or a photoelastic elasticity materials, which includes Columbia resin, Homolite 100, polycarbonate, epoxy resin, urethane rubber, and so on. So these materials which will be considered as a photoelastic material to study the behavior of the member under loading conditions. Now we shall discuss the individual what you call as material for and its application. See, the Columbia material, the Columbia resin, which have the range of CR, we can call it as CR 39, 39, 30 and 31. The Columbia resin is an alloy digital carbonate which is produced by reacting phosphogene with the diethylene glycol to obtain a chloroformate, which is then esterified with the alcohol to yield as a monomer. Therefore, the monomer is a polymerized by heating in the presence of catalyst, and the catalyst which includes benzol peroxide, and the resultant sheet is a crystal clear product. So the casting operation is performed in such a manner that the final product in the sheet forms which has surfaces of optical quality. But actually this is the predominant advantage of this material, that is CR39, namely that is available in large sheets of 48 to 60 inches of number of different thicknesses with the surface finish which is nearly optically perfect. So the material is widely applicable for many of the photoelasticity applications. Along with this one, the material has a good what you call as brittle property, and which is difficult to turn out by any other milling operations, but it can be readily machined by routing and a high quality photoelastic model can be usually produced within an hour. So this Columbia resin material finds its major applications because of these properties. And along with this one, which can be by routing operation, we can make enormous amount of what you call as machine tools, or for the machine tools the products within an hour. See, this material has a relatively low fringe value indicating sensitivity, but its sensitivity index is very low compared to the other one which can be considered as low stress value, at which it becomes non-linear. Therefore, the CR39 exhibits appreciable creep, and the material fringe value must be determined as a function of time. So this is, and the material is less prone to the what you call as time edge effects than epoxy, but more susceptible to time edge effect than the polymers. And here for these susceptible what you call as time edge effect, then the polymers are polycarbonate, and because of this reason we can be replaced by the polymers as well as the polycarbonate materials. The second material is Homolite 100. See, the Homolite 100 is a polyester resin which is cast between two plates of glass to form very large sheets. And here the surfaces of the which are the commercially available sheets are of optical quality. And along with this one, the material is free of residual stresses. And the models can be machined by a routing operation. And however, since the material is extremely brittle, edge chipping will be a difficult in what you call as formation, or difficult in what you call as machining operations. So Hemalite 100 does not exhibit appreciable creep. Therefore, the material fringe value can be treated as constant for loading times in excess of 5 to 10 minutes. But since the moisture, because of the moisture absorption which is very slow in this material, time edge effects do not come apparent for the several days, even under very humid test conditions. Therefore, this material exhibits both a low fatigue of metric of U and low sensitivity index, and along with this one it has the other property, that is high fringe orders can be achieved without fracturing the model. This is what the advantage and of this proper material. The third material is polycarbonate. See, polycarbonate is an unusually tough and ductile material. Basically it is a tough and ductile material, and material in the sense it is a polymer which yields and flows what you call as flows prior to the before to the before to the fracture of the system. It is also known by the trade name as Lexan in the United States. And polycarbonate exhibits both at high fatigue and a high sensitivity index. It is relatively free of time edge effects and exhibits very little creep at room temperatures. This is what the advantage of this polycarbonate. For this reason, and along with this one, it is a tough and ductile material, which is compared along with this, it is a lightweight material. And polycarbonate is a thermoplastic and is produced in a sheet form by an extrusion process. And here it is available in the material is available in large sheets with reasonably good surface characteristics. But the extrusion process usually produces some residual bifringence in the sheets. And one thing is that annealing for an extended period of time or near to the softening temperature is required to eliminate the residual bifringence. And the polycarbonate material is also difficult to machine. Any significant heat produced by the cutting tool will cause the material to soften and deform under the tool. And the best method of machining is that routing can be performed only under water, and sand milling is preferably impossible. And the bifringence introduced in the plastic state is permanent and is locked into the material on a mono or what you call as on a molecular scale. Therefore, this behavior makes the material suitable for the meticulous many three-dimensional photoelasticity studies. Next one is the epoxy resin. See, the epoxy resins were first introduced in photoelastic applications, that is in 1950s, when they were employed predominantly as materials for three-dimensional photoelasticity. See, this three-dimensional photoelasticity we will be discussing in the next module. Now, meanwhile, this material, understand, this material is been applicable majorly for the three-dimensional photoelasticity analysis. However, a brief review of their properties indicates that they are also quite suitable for use in the variety of two-dimensional applications. See, the commercial epoxy resin are considerations products of and can be products of what you call as polyhydric phenol. The basic monomer can be polymerized by using acid and polymerics. Also, we can call it as polymerics. In general, curing with the acid requires high temperature than curing with the polymerics or polymerins. And here, this material has a wide variety of epoxy materials which can be cast into the sheet form. And the basic type of the basic monomer have the curing agent, and the percentage of curing agent relative to the basic monomer can be varied to give an almost infinite number of epoxy materials. And one thing is that this epoxy can be cast into sheets which are light in amber, what you call as amber, or in appearance. However, the optical quality surfaces are difficult to produce, so the surface finish by fly cutting or by milling is frequently required. And the important thing of this epoxy resin is the epoxies are usually characterized by brittle materials, but they are easier to machine than the polyesters. Polyesters in the sense the grade between that is CR39. And most of the epoxies exhibit better optical sensitivity than Homalite 100 or CR39. And the next one is urethane rubber. The urethane rubber is an unusual photoelastic material in that it exhibits a very low modulus of elasticity, in the sense that is 3 orders of magnitude lower than the other material listed, and is very high sensitivity, which has an indication of FA values that is less than the 1 lb per inch or 0.175 kilonewton per meter. And this material can be cast between glass plates to produce an amber colored sheet with optical quality surfaces. And here the material, except for its very low fatigue of merit, the material ranks relatively well in comparison with the other material listed. And here the urethane rubber has a strain sensitivity with a very low strain sensitivity compared to the other what you call as materials of photoelasticity. And the material can be readily machined on a high speed router, but one thing is that it must be frozen at liquid nitrogen temperatures before its surfaces can be turned or milled. And other thing is that the material is particularly suited for demonstration models only, and the loads applied by hands are sufficient to produce the well-defined fringe patterns. And in the absence of type what you call as time edge effects, which permits the models to be stored for years. And along with this one, the material is so sensitive that the stress that it can be used to study body force problems in fringe multiplication techniques are employed with thick models. Finally, urethane rubber can be used, which can be used for models in dynamic photoelasticity, where its a low modulus of elasticity has the effect of lowering the velocity of the stresses and less than, that is 90 meters per second, as compared to the CR39. So this low velocity stress waves in urethane rubber models are easy to photograph with moderate speed framing cameras. That is what the major applications and major what you call as implementation of this material. And the next one is, these are the major five what you call as photoelastic 2D photoelastic materials, and along with this one we will discuss what are the different material properties of these materials. In consideration with the materials, why we need one of the most important factors is that in photoelastic analysis is the selection of the proper material, and here the material which you are selecting should be unfortunately a perfectly ideal photoelastic material. And here such a what you call as perfectly photoelastic material doesn't exhibit at all, and the investigator, whatever the investigator who is investigating on the photoelasticity models, must select from the list of available materials, and those available materials already we have discussed. And the quantity of photoelastic materials used in year is not sufficient to entrance a chemical company. And the following and the materials which are sensitive, the consequence what we are selecting, the development of the photoelasticity for the analysis of problems has been due to the identification of suitable materials for models from among the plastics available in the market. Therefore, the selection of suitable material for preparation of photoelastic materials models forms an important step in the photoelasticity analysis. And it is difficult to find a material that satisfies all the requirements. But however, some of the important properties of an ideal plastic material are classified in the upcoming slides. Now, the properties of photoelastic materials have been listed here, and here you can observe under optical on the characterized into different categories. First one we will be discussing, that is optical properties. In optical properties, these are the transparency, sensitivity, linearity. These are the major three what you call as properties in which comes under optical properties. Second one is the structural properties, and structural properties which includes isotropy and homogeneity. And third one is the mechanical property, and mechanical property which includes the mechanical properties like modulus of elasticity, Poisson's ratio, ultimate strength, yield limit, and creep. And the fourth one is the thermal properties. The thermal property which includes temperature sensitivity and thermal conductivity, and along with this one we have the exothermic reaction. And fifth category is the production properties. The production properties which includes the machining properties such as castability, machinability, shrinkage, stresses. And the sixth one is environmental properties. The environmental properties which includes curing period and timeage. Now these properties are the majorly required properties for a 2D photoelastic materials. And next we will discuss with one by one. That is, the first one is transparency. See, transparency for a photoelastic material. In almost all normal applications, the material selected for photoelastic models are transparent plastics. These plastics must be transparent to visible light, otherwise they need not be crystal clear. This transparency requirement is not difficult to meet since most polymeric materials are colored or made opaque by the addition of filters. So, the raw materials in the basic polymer, although not a crystal clear, not as crystal clear, are usually transparent. So here what happens in certain special applications which require a study of the stresses in normally opaque materials, which includes germanium or silicon, an infrared polariscope has been used, and a few materials which are transparent in either the ultraviolet region or infrared region of the radiant energy spectrum. Polariscopes can be constructed to operate in either of these regions if the advantages can be gained by employing the light, what you call as light, with very short or very long wavelength. However, for stress analysis purposes, the visible light polariscopes are quite adequate. And so, this is the most the required what you call as property for a two-dimensional photo analysis. Second property is the sensitivity. So everyone knows the sensitivity based upon for every applications. That is in nature, how does it senses be depending upon the input load? What is the output with respect to the input? Now, as high sensitivity photoelastic materials is often desirable since it increases the number of fringes, and which can be observed in the model. The models which you have seen in the previous fringe patterns, and if the value of the sensitivity for a model material is low, a satisfactory fringe patterns can be achieved in the model with relatively low loads. So, and this feature reduces the complexity of the loading. And here, in case of the bifringent coatings, which will be discussed in the later classes, that is what in the module 3, in the module 4, that is three-dimensional photoelasticity, a material with low value of what you call as sensitivity is essential to reduce errors, and which is introduced by the coating thickness. And one thing is that the photoelastic materials are available with the values which range from less than 0.2 to 2000, what you call as 0.22, or you can consider it as 0.035 to 350 kilonewton per meter. And here the material with the value of sensitivity, that is in 0.0005 mm, would greatly enhance the applicability of the bifringent coating method by photoelasticity. This is the in brief explanation of the property that is called as sensitivity. Third property is the linearity. And many of the linearity, which includes, depending upon the loading applications, the linearity of the behavior of the member. So, photoelasticity models are normally employed to predict the stresses which occur in a metallic prototype. Since the model to prototype scaling must be used to establish prototype stresses, what happens here? The model material must exhibit linear stress strain, what you call as stress strain relationship, and optical stresses and optical strain properties should be exhibited in the linearity. And for few data analysis which are available in the what you call as optical strain relationship, however, since the photoelasticity method is usually employed to determine the stress differences, and typically stress strain curves and fringe orders can be determined. And one thing is that at higher levels of stresses the material may exhibit non-linearity effect. For this reason the higher stress levels are to be avoided in photoelasticity tests which are associated with these non-linear materials. And fourth one is the isotropy and homogeneity. Most of the photoelastic materials are prepared from liquid polymers by casting, and that is a process by casting between the two glass plates which form the model. But when the photoelastic materials are prepared by casting process, the molecular chains of the polymer are randomly oriented. They are randomly oriented and the materials are essentially isotropic and homogeneous. And however, these materials, that is photoelastic plastics, are rolled and stretched during the production. In both of these production process, the molecular chains are oriented in the direction of rolling or stretching. Therefore, these materials will exhibit anisotropic properties. See, the anisotropic properties include both mechanical and optical properties. And therefore, these should be avoided in any these materials, what you call as this material property should be avoided in any plastic, what you call as photoelastic application, except where an isotropic material properties are required. So this is one important property for any photoelastic materials, and majorly these properties are avoided in many of the components. And one thing is that here whenever the material anisotropic material is required, then we will be considering such kind of property in a material. Third one, that is the fifth one, is the creep. See, many of the materials, what you call as photoelastic materials, where the creep analysis, that is depending upon the time duration, what is the what you call as failure in the member. Unfortunately, most photoelastic materials of polymeric base creep both mechanically and optically over the time associated with photoelastic analysis. See, one thing is that depending upon the timing as well as the loading, there is a what you call this deterioration of the material, or there is a failure of the material depending upon the loading as well as the time. That is a time dependent loading. And because of these effects of mechanical and optical creep, polymeric materials cannot be truly characterized as elastic materials, but must be considered for certain applications. And one of the first attempt to formulate the mathematical theory of photoelasticity was made by Midlin by considering a generalized viscoelasticity model, which was consisting only about the elasticity elements with the shear modulus. And with the evident from the results which have been obtained from Midlin were useful, that is useful for the result that the optical response exhibited by the photoelasticity model, and which depends upon the viscoelasticity properties of the model. And here this is the majorly required property, and due to the effect of mechanical and optical creep, polymeric materials cannot be truly characterized as elastic materials. And next important what you call as property is modulus of elasticity and proportional limit. See, the modulus of elasticity or Young's modulus. The modulus of elasticity is important in the selection of photoelastic material because the modulus itself controls the distortion of the model due to the applied stresses. And if a model destroys, the geometry of its boundary will change and the photoelasticity solution is no longer accurate. So for this reason, the modulus of elasticity is important for a photoelastic material. And if a model distorts, the geometry of its boundary will change and the photoelastic solution is no longer accurate. And along with this one, errors of considerable magnitude are produced whenever the modulus of elasticity is being impacted on the model, and which will produce a model distortion, where a small changes in the boundary counter are identified while determining the stress distribution. See, let us consider one example as a strip. That is a small strip with a very sharp notch theoretically, which will be having a very high stress concentration at the root of the notch. And if the model distorts under loading conditions, the sharpness of the notch is decreased and the experimentally determined stress concentration is reduced. And here one thing is that in this instance, the stress distribution is a function of the penetration of the bearing area of the loading point. Obviously, the modulus of elasticity is influenced in controlling both of these quantities. And next property is machinability. Say machinability, it's the ability of the machine to be to remove the material on the surface. It's the ability to do for the machining operations. See, photoelastic materials must be machinable, and if they are not able to machinable, then it is very difficult to manufacture such kind of components. So in order to form the complex model which are employed in photoelastic analysis, ideally it should be possible to turn or to mill or to routing operations can be done, turning operations must be done, and drilling operations. Along with this one, the grinding operations should be done. And here these operations which are done on the plastics, although machinability properties may appear to be a requirement, it is often extremely difficult to machine a high quality photoelasticity model. Why? Because the action of cutting tool on the plastic often produces heat, which is coupled with relatively high cutting forces. As a consequence, both stresses due to machining can be introduced permanently into the model. So because of here mechanical property as well as a thermal property which will be induced in the material, and if this is induced in the material, then the properties of the photoelastic material will be varying. So in machining photoelasticity models, care should be taken to avoid high cutting forces and the generation of excessive amount of heat. So for these conditions, the requirements, what you call as best requirements, can be accomplished by using sharp carbide tip tools or air cooling. Along with this one, sharp carbide tips can be used, tools can be used, and along with this one, air cooling can be done. And along with this one, we need to have a light cuts coupled with relatively high cutting speed. But for two-dimensional applications, complex models may be routed from almost any thermosetting plastics. In this machining method of rotor motor is used to drive a carbide rotating file. And the photoelastic model is mounted to a metal template which describes the exact shape of the final model. And with this, what you call as the other thing is that the metal what you call as template, which is guided by the oversized diameter pin, which is coaxial with the rotatory file, the rate of feed along the boundary of the model is carefully controlled. And here the important thing is the photoelastic model is mounted to a metal template which describes the exact shape. One thing is that, and this one, the successive, after considering the metal template which will be guiding by the oversized diameter pin of the file, the rate of feed along the boundary of the model is carefully controlled by moving the model along the pin by hand. Then what happens? The successive cuts are taken by reducing the diameter of the stationary pin until it finally coincides with the cutter diameter. So, by using this technique, satisfactory two-dimensional models can be produced in less than 1 hour. So this one, the machinability property in certain what you call as photoelastic materials is desirable, and depending upon the application, whether the photoelastic material is subjected for what you call as compressive loadings or it is subjected for tensile loading. Depending upon the loading conditions, the machinability of a particular material is necessary. So these are the major properties which are being required for a two-dimensional photoelasticity materials. And with this, we have discussed what is photoelasticity from the beginning, what is photoelasticity, photoelasticity behavior, and what we call as polariscopes we have discussed, and photoelasticity materials we have discussed, and the different materials of different photoelastic materials and their applications we have discussed. And for these photoelastic materials, we also discussed the different what you call as different photoelasticity material properties, and we have listed the 6 machinability property called as properties of photoelasticity also we discussed. By this what you call as properties of photoelasticity material, the module 3 photoelasticity, that includes the photoelasticity, and the module 3, that is chapter 3 and chapter 4, two-dimensional photoelasticity, has been completed, and the further classes will be taken over. And here this completes the module 3. Thank you.